I'm rubbish. I like rubbish bin. Landfill is my final destination. Whoa! Rubbish bin, I love you. Ooh, I go to landfill by truck. According to the data from Hong Kong government, the textile waste increased yearly. Most of the textile waste disposed to landfill. The recovery rate is very low. Reuse is the main recovery method for textile waste. I'm rubbish after reuse. Send me to landfill.
You're not rubbish, get out from me!
Whoa, rubbish bin. Why? I'm useless.
Of course not, let me show you a new value.
Some research shows that there are 40% cellulosic fiber and 60% man-made fibers. Therefore, recover the cellulose in textile waste is one of the methods to treat the textile waste. Let me introduce the enzymatic hydrolysis of cellulose in cotton. It includes 3 steps. Pretreatment. Enzymatic hydrolysis from cellulose to glucose. Fermentation of glucose to form bioethanol.
So let's talk about the pretreatment process. The characteristic of textile waste, which includes accompanied by man-made fiber, in high-ordered crystallized structure, and well-organized construction of polyester and cotton fiber. These may greatly reduce the efficiency of enzymatic hydrolysis. Therefore, some pretreatment processes are necessary before the process of enzymatic hydrolysis. There are in total 3 pretreatment methods we are going to discuss. They are alkaline pretreatment, acidic pretreatment, and ionic liquid pretreatment. Sodium hydroxide is the alkali that will be used as alkaline pretreatment. Sodium hydroxide can not only reduce the crystallinity of cellulose by dissolution, it can also penetrate the crystalline and amorphous area of the cellulose, disrupt the neighboring crystalline regions, swallow and dissolve the cellulose of textile waste in certain concentration, and cause changes of crystalline structure. In addition, it was discovered that the presence of urea, thiourea, or the mixture of them will also enhance the process of dissolution of cellulose in sodium hydroxide by ensnaring the free water and preventing the reassociation of cellulose molecules, which means higher yield of hydrolysis can also be performed. From the experimental result, it was discovered that the yield of enzymatic hydrolysis was greatly enhanced from 46.3 to 70 to 91%. At the same time, the highest hydrolysis yield was also observed when with the usage of urea, thiourea at -20 degrees Celsius, or the mixture of them at 0 degrees Celsius. Among all the other pretreatment methods, alkaline pretreatment is one of the most common and effective pretreatment methods, and its low cost make it economically feasible. However, its high concentration may bring negative impacts to the environment, and since cellulose from textile waste is unable to dissolve completely in sodium hydroxide, this may result in incomplete separation of cellulose and polyester. Phosphoric acid is the acid used in the acidic pretreatment method. Similar to sodium hydroxide, phosphoric acid can act as a solvent for crystallized cellulose dissolution. The process of diluting phosphoric acid can reduce the degree of crystallinity and polymerization and increase the surface area of the cellulose in order to raise the efficiency of enzymatic hydrolysis. From the experimental result, it was discovered that when longer pretreatment time, which increased from 12 hours to 24 hours, 100% separation of polyester can be made. However, degradation of glucose also happened, which resulted in the decrease of enzymatic hydrolysis yield. In addition, from the experimental result, it was discovered that phosphoric acid with 85% concentration at 60 degrees Celsius reached the maximum yield of cellulose and polyester recovery and enzymatic hydrolysis yield. Moreover, the yield of enzymatic hydrolysis has significantly improved to 67 to 75%, but it is lower than the 70 to 91% from the alkaline pretreatment result. Comparing with alkaline pretreatment, acidic pretreatment is a non-toxic and non-corrosive pretreatment method. However, its hydrolysis performance is weaker than sodium hydroxide. At the same time, prolonged process will cause degradation of cellulose recovery. Acidic pretreatment cannot bring out dominant benefits but causes lower efficiency of enzymatic hydrolysis. It seems that it's a worse pretreatment method than the alkaline pretreatment. Since some challenges need to be faced with the usage of alkaline and acidic pretreatments, ionic liquid pretreatment is also studied. Although only a little of ionic liquid is found to be non-hazardous and the shortage of large-scale energy-efficient recycling method, some ionic liquid like N-methylmorphine and oxide and sodium carbonate will still be used. NMMO is one of the cellulose solvents used as industrial cellulosic fiber spinning process because up to 30% of cellulose dissolves in it. Better than the acidic pretreatment method, NMMO would only change the crystallinity of cellulose but not degrade the cellulose. Better than the alkaline pretreatment method, NMMO is non-toxic and fully biodegradable with moderate working conditions. NMMO as a cellulose solvent, it is able to perform very high conservation yield of high crystallized cellulose. At the same time, it can perform similar and even better enhancement in hydrolysis. However, it is discovered that it is only economically feasible when 98% recovery are achieved, which means large scale of energy-efficient recycling method is needed. Sodium carbonate, which is a much cheaper solvent, is therefore be discussed. Since cotton fiber is found to be more stable in alkaline environment than in acidic environment, sodium carbonate can provide a stable situation for the cotton fiber. Similar to NMMO, sodium carbonate is an environmentally friendly chemical, and it can bring no destructive influence to the cellulose of cotton. Sodium carbonate is very easy to be handled and recovered. No large scale of energy-efficient recycling method is needed, which means it's much cheaper than NMMO. Besides, it can provide a weak alkaline environment and bring great enhancement in hydrolysis, but it is lower than the NMMO. Let me introduce the principle of enzymatic hydrolysis.
Whoa! Enzymatic hydrolysis from cellulose to glucose includes three enzymes: endoglucanase, exoglucanase, beta-1,4-glycosidase. The optimum conditions for the enzyme is 45 to 55 degrees Celsius and pH 4 to pH 7. The whole process includes three steps. The first step, the endoglucanase will break the pretreated cellulose to cellulodextrin. The second step, the exoglucanase will break the cellulodextrin to cellulose. The third step, the beta-1,4-glycosidase will break the cellulose to glucose. Well, I can be converted to glucose now.
Not yet, still have problem.
Commercial enzyme is very expensive, and the textile waste content is varying. Oh, how to solve this problem? The problem can be solved by solid-state fermentation with using the textile waste to produce enzyme we need. Solid-state fermentation is fermentation process occurring in the absence or near absence of free water. The pretreated textile waste together with the solution with aspergillus niger CKB fungi will undergo incubation with moisture. Then the enzymes produced will be extracted. The extracted enzyme will be used to hydrolyze the pretreated textile waste to form glucose. The final yield of glucose was found similar to the yield of using commercial enzyme. Finally, the glucose will undergo fermentation to form ethanol. Well, I find my value!